So good evening, everyone. Thank you so much for this wonderful introduction. I'm here. So thank you, Don. Thank you, Justina, and everyone for joining me despite the lovely weather, and which surely was an attractive alternative. So let's try to make this hour together productive and exciting. Hopefully, I will try to share with you some of the work and research that I have done in the last few years. Some of the things I will show tonight are also really a kind of first so that I'm pleased to share with you. It's important to just also show that it's not just me. We are very much a duo, and the whole practice and research has been conducted in partnership with Claudia Pasquero for many years now. We've done a few things that caught the attention, I think, of the audience, which of course relate to the topic that I think everyone is concerned with these days. And this was the first ever urban algae canopy in Milano, 2015, and the first permanent biotechnological dwelling in Astana for the Expo, 2017. Large 3D printed photobioreactor, which was presented in San Pompidou, 2019, and now it's in Tokyo, a Mori Art Gallery. And we got some honorable mentions here for the world-changing idea by Fast Company for the PhotoSynthetica Dublin. Interestingly enough, this project went rather viral. This is what the BBC said about it.
If we want to make our cities greener and save the planet.
So, save the planet, says the BBC.
Here in East London, a team of architects and scientists are busy developing technology
Claudia is the scientist
to change the look of cities everywhere and help save the planet.
I'm the architect
it
here.
involves these biocurtains. They can be fitted to the outside of any building. They are filled with algae. Taken from their natural home, they are treated in a lab. Gel is added to optimize their performance. Why do this? Well, algae are very naturally efficient at turning carbon dioxide into oxygen. When the sun shines on the curtains, photosynthesis takes place. Polluted city air is drawn in from the bottom of the curtain, the single-cell algae absorb the carbon, and oxygen is released at the top. The inventors say it is an effective way to cut down greenhouse gas emissions in cities.
This is effectively an extremely efficient way to introduce photosynthesis within the built environment.
In terms of air cleaning power, he reckons one of these curtains is equivalent to a mature tree. So far, the biocurtains have been installed at the Customs and Revenue House in Dublin, and most recently, the House of Nobility Palace in Helsinki. However, the scientists behind the idea acknowledge that curtains would have to be adopted on a very large scale to start making any meaningful impact.
It's low, so UK is aiming at becoming carbon neutral by 2050. London has got it in its plan. We have to, at the same time, reduce the amount of carbon that we emit, but also actively absorb.
There are some drawbacks to these biocurtains compared to trees. At the moment, the curtain material is only 70% biodegradable, the rest plastic. Also, as the algae grow, they have to be harvested on a regular basis, which requires maintenance. This is one reason the curtains work out more expensive than trees, though they take up less space. But for the scientists involved, this project is also about changing our relationship to nature.
CO2 is not negative per se. We cannot breathe it as human beings, but is a nutrient for microalgae. So we can create an alliances with microalgae to be able to interact with the air of the city, with the metabolism of the city, and change it in a positive manner.
So I wanted to show this because obviously this is the way our work is portrayed. And this is the kind of antidote, in a way, to that portrayal, if you want. What is it? Oh, God. Sorry, something is happening here. I think this was... Keep going. I knew it was going to be a mess, this thing, but I tried nevertheless. Okay. We are back. This is what we do at the lab, Urban Morphogenesis Lab in London, which Claudia leads. And that is engaging with a paradigm of nature that is somehow broadened to include all different forms of nature, but also the idea of biological intelligence and biocomputation. So why I showed you these two videos is because it's a part of our current interest to, of course, engage directly with the issues that we are confronting today. But at the same time, as researchers, as academics, we wish to try to expand the paradigm within which these issues are engaged with. Because we believe that the expansion of the current ecological green paradigm is necessary to render our efforts more effective in the years to come. So in that sense, I would like to underline tonight with this lecture some of the key aspects of this effort, let's say, of expansion, of extension of this paradigm. And the first one starts really from the definition of nature and this idea of greening or regreening that we hear continuously in the news, and that is applied to everything that engages with this paradigm. And I think that there is a certain paradox, if you want, within this kind of green ideology, that it proposes what I call the sanitized version of urban nature and renders it, in that sense, ineffective towards establishing a more profound engagement with the circular economies of matter, information, and energy that are at the core of a truly sustainable paradigm. And again, I think here to understand why this is the case, we may need to go back a little bit and realize that, let's say, at the root of the core of modern master planning is the concept of sanitation. It's the idea to use a kind of rational approach to separate functions in a way that potential conflicts between zones of production and zones of leisure and residential areas and versus industrial areas can be managed without problem. But essentially what in time has occurred is that the separation of flows has also become a separation of a space, kind of removal of these elements that have to do with the extraction and processing of resources, and the one that have to do with the collection and recycling of the resources outside of the city, and if you want, also outside of our site. So in our daily life, we don't have a perception of these flows, and therefore they tend to disappear from our consciousness as a rather fundamental level. So this is, I think, for me, the origin of what we may call the metabolically linear city that you see somehow illustrated in these diagrams. And we all know that in order to close the loop, to recirculate what comes out on one side and into a resource that is useful for the city, we need processes that at the moment, in the vast majority of the cases, are still taking place in the biosphere. So we offload this task of recirculating resources to the biosphere. But as we know, these are numbers that everybody is now kind of used to see. The growing urban population means that this task of recirculating the emissions of our urbanizing society is no longer possible. And the biosphere is reaching a tipping point, and that's what we inevitably are confronting these days. Now, something that is interesting is that, as you have seen perhaps very clearly also here in Australia, despite overwhelming evidence, still governments struggle to act and to respond appropriately to these emergencies or to these tipping conditions. And I always wonder why that's the case. And of course, there are multiple reasons that we may look into the kind of political realm, of economic realm, the power of the petrol industries and so on and so forth. But I think that for me there is one element that is often if you want, overlooked, and it's really related to this conception of nature that we all somehow share, and that is, let's say, inherited from, we shall say, modernity. And so I think today we came to believe that such rationally organized environments that we considered our modern living habitats apply to the biosphere as a whole. So in a way we have a machine-like model of nature, of the biosphere, that is dominated by this idea of equilibrium. So when we talk about carbon neutrality or regreening, we think that it is somehow possible with our current logics to, take a situation like this one and, rebalance it out. So if we are absorbing more and emitting less, we can bring the system of the biosphere back into equilibrium. And so in that sense, we can solve all our problems. But unfortunately, that doesn't really work like that. We know from science and we know from field work that the city, as well as the biosphere as a whole, is a complex nonlinear system, which is composed of billions of feedback loops, and change is its defining quality, and equilibrium is always precarious, is always dynamic. So there is at any point the possibilities for the system to switch to a different kind of equilibrium, which may not be very favorable to us. So in that sense, it is very important and imperative for me to use our, let's say, power as designers to bring back into a certain level of consciousness this kind of, which we may call this dark side of ecology, that fundamentally embodies the other side of the loop. So not the side of growth and proliferation, but the side of decay, digestion, death, dissolution. These are some of the most fundamental processes that we encounter in the biosphere that are part of the cycle of life. And they are also very much part of the urban sphere or of the cycle of our cities. But of course, we tend not to see them, or we don't necessarily want to see them. And typically they are not green in color, and they are not green in their appearance. So essentially, one thing that we have discovered in these years of research is that when we look at this particular site of the cities, and this is just an example from a recent research that we are doing with the United Nations Development Program in Accra, Ghana, which is one of the sites where the big amount of the e-waste generated by Europe and the US also is a kind of offloaded. If we look at this, we realize that it is at the nanoscale or the microscale, I should say, of particles and molecules and microorganisms that this kind of exchange between, let's say, the urban metabolism and the natural metabolism occurs. Is this moment in which the kind of so-called pollutants begin to enter the biosphere. That is a kind of critical liminal zone that we think should be brought to the attention and designed to a certain extent. And so this is why my practice now investigates the resolving boundaries between city and nature, a territory that we have named urban sphere. In the urban sphere, nature exists in forms other than its idealized green, and architecture also comes alive. The architecture of the urban sphere can no longer be described typologically or through separate scalar and material domains, and it is by definition distributed and transcalar. So this new perspective gives, I think, our discipline a radical expansion of its scope, which I embrace with my practice and I intend to contribute in the future. The urban sphere can be defined as the global apparatus of contemporary urbanity, a concept that calls for architects to curate knowledge across the domain of science, art, and engineering. In this conception, the architect's ability to see and think spatially is central to the articulation of new forms of ecological intelligence. Our research therefore focuses on building architecture, installations, and digital protocols, testing the human's interaction with non-human systems. And so this is how we came to work with these microorganisms, with this particular, let's say, layer of nature that is often not visible, but that somehow represents this very critical interface. And so one of the projects that we have been working on for several years now, and that has become let's say now almost our kind of a more common and known line of inquiry, which is called PhotoSynthetica. It's really started from a kind of investigation into the microorganisms called the cyanobacteria, and also photosynthetic algae. And these organisms have a quite a unique way of growing, which makes them extremely effective or efficient. And sometimes we forget that, in fact, they are the one responsible for absorbing most of the CO2 in the biosphere. And these are organisms that have been around way before the dinosaurs were on this planet, and of course, way before than we were here too. So they have evolved, we could say, a very unique ecological intelligence or biological intelligence that makes them extremely resilient. And that's why we see them growing in every kind of environment, even the most polluted environments, so the one we consider polluted, they are fertile for them. This is a picture actually from the Baltic Sea. You can see a little boat in the middle. The scale is quite humongous, and it kind of describes one of these episodes of algae blooming in that sea, and how that in fact can take really extreme proportions. But let's say for us the interesting element is as designers to locate our role, I think. And for us, this has become very much the role to design a kind of interface, if you want, on an artificial habitat whereby these organisms can now grow as a part of the urban realm and therefore activate its ability to photosynthesize resources. The interesting thing is that through this operation, we can maybe reconnect what we call the green and the dark side of ecology. These are kind of closed-loop cycles. And when you do that, we discover there are multiple interactions in buildings that can be activated by the intelligence of these organisms. So the microorganisms tend to grow faster within our artificial habitat than in the wild, precisely because what the building emits, like heat and CO2, is a nutrient for the algae themselves. And in exchange, of course, they can provide screening potential and biomass as well as oxygen. So there is a kind of a new level of symbiosis, we can say, between them and the living organisms that inhabit the building itself. The idea of efficiency as well is interesting, because when you move into the micro scale, you deal with organisms that don't have to spend energy into maintaining a complex infrastructure like the one of trees. So of course trees are beautiful, but at the same time when you try to integrate them in a dense urban realm, they often fail, because they need space, they need to connect to each other in order to perform effectively. So that's when, let's say from the point of view of design and engineering, we find that there is opportunity there for imagining a new layer of high-tech nature, if you want, that can inhabit the urban realm and increase its ability to photosynthesize. The other fascinating aspect is the idea of remetabolization. So when the pollutants from the air or the carbon for the molecule of carbon dioxide enter this layer of curtain and come into contact with the algae, they are captured, and the algae use them to build biomass, essentially to grow and to replicate. And the biomass is, of course, useful for multiple applications that are already evolving in the industry, like food, biofuel, bioplastics. So essentially, there is a kind of a remetabolization of what we know as nutrients into raw material for new products and new processes. Which means that essentially we are transforming what we now understand as pollutants into potential raw material. Now, the idea is that, of course, we are designers. Our role is to try to imagine as many scenarios as possible for the integration of these systems and organisms, and that's what we have been doing in the last few years, just building as many test beds, as many pilots as possible to really not only imagine, but also be able to measure and understand the potential application of these systems in the real world. So these are some case studies as a kind of temporary cladding system during the refurbishment of the Nobility House in Helsinki. This is in Aarhus in 2017, during Aarhus Capital of Culture, which became a kind of a piece of sculpture activating the urban space near to the port of Aarhus. And so, again, playing with the idea of nature as infrastructure in this case. This was one of the early prototypes for Milano, where we constructed one of our largest urban canopies, which you see described here in this video. Here you get also a little bit of an idea of the way the system works. This is one example in which the algae are actually flowing within the system, and so they are essentially pumped on the top of the canopy that by gravity come down, and they inhabit these photobioreactors, these membranes where they are essentially coming in contact with both solar radiation and oxygen. The system also was integrating sensors to measure the parameters of life of the algae, so temperature, pH, salinity, as well as the presence of humans around them, and therefore understanding the potential of these as a kind of microclimatic moderator.
Really challenge us to understand.
This is another one of these applications where we dived into the potentials of 3D printing and also of gardening, as you can see. But the idea here was that through 3D printing we can articulate matter or the substratum at a scale that is comparable to the scale of the microorganism. So potentially we can now not only somehow encapsulate these organisms into an enclosed environment, but really create a kind of hybrid matrix where the natural and artificial components are no longer clearly distinguishable. So this is a porous system which exposes the algae to flow. The algae are kept in place through a biogel solution that jellifies the medium, so they are no longer liquid, but they are still wet, and so they can live and thrive. And then they are held in place by this 3D printed substratum that effectively exposes them, maximizes their exposure to light and to the exchange of oxygen and CO2. This is the view from the inside of this niche. So this project also started to travel the world a little bit, and at some point a couple of months ago landed in Tokyo. And here we had a really exciting opportunity to exhibit it in the Mori Art Gallery, which is on top of the Mori Tower, the 53rd floor. And the room where we exhibited this was very much a kind of large window opening up on the landscape or cityscape, I should say, of Tokyo. And this is not a Photoshop, actually. It's a real picture which somehow played with the reflections of the glass, and you can see the prototype kind of entering the urban realm of on a different scales. And of course, this became also part of our kind of exploration with the idea of imagining or reimagining a new singularity in the urban landscape. So a scale where these processes of filtering the air, capturing CO2, extracting biomass for useful processes could be big enough to actually have an impact on both the urban atmosphere and also in the creation of new economies based especially on this new closed metabolism. So new circular economies, if you want, in the city. And this is some views of what may be the kind of large urban interior, biotechnological interior. This became also a kind of interesting experiment that will be exhibited in the Biennale in Venice, the Corderie dell'Arsenale this year, where we will try to essentially prototype one unit, one of these large comps of the PhotoSynthetica tower. But there is one of these units that we managed to build already in Astana in 2017, and this is one of actually the first permanent project of this kind. And essentially, the idea of the biotech hut was to test the possibility for a self-sufficient dwelling based on the biotechnology of the algae. The plan is quite simple. There are these three environments that are kind of loosely and interconnected through this flow. So the algae also manifest themselves, represents the flow interconnecting the environments. The three environments relate to the three key ways in which we engage with nature. So science, rationality, the space of the lab, where you use the tools of science to dive in the microscale, learn about the biodiversity of the algae, the properties they have, what you can do with them, and effectively begin to measure, quantify the potential that they have. Here was the amount of energy that we could extract from the algae in the biotech hut. We had around 1,600 liters of cultures there. We generated 1 kilo of dry algae per day and releasing more or less enough power for an average UK home. This is 10 kilowatt. The space adjacent to this was the space of art experience, so we called it living, and this is where the same process, the same kind of relationships explored through a completely different type of interaction, experiential, intuitive, and artistic. So this was dominated by this piece that we created to kind of hang in the middle of the room, which essentially was enabling visitors to feed the algae with CO2 by pumping manually and then immerse themselves into the sculpture and essentially breathe the CO2 the sculpture were emitting and be surrounded by this sculpture. The exchange oxygen CO2 was about 2 kilograms per day, and again this is equivalent of what 32 large trees can do, and everything integrated in the skin of the biotech hut. And finally, the final space was the garden, and it's a space of craft, of production. So that's the third way to engage with these processes, and where we actually use our hands and learn how we can extract something useful from it. And this was also a space that was kind of supported by the sensing and the interface, which would suggest critical moments and how to effectively maintain the cultures alive and healthy. And also where we were extracting the wet algae, which, as we know, contains proteins, especially the chlorella, which we were growing there. We calculated that there were around 600 grams of protein being produced every day, which is the daily intake of 12 adults. So if we believe that there is a kind of imperative to switch to new ways of feeding ourselves without meat-based proteins, this could save the life of 8 cows. Essentially, this is the construction system. As you can see, multiple layers, laminated wood and Bencor, the structure, but the fundamental elements were the glass pipes or the photobioreactors where the algae would grow, kind of coiling around the room, so effectively surrounding the visitors of the space. So something that is interesting, I think, is fundamental when you begin to implement these kind of logics is that architecture becomes capable of synthesizing resources. So it's no longer just a container of programs, which traditionally we would call machine for living, but becomes itself a dynamic process of production, and therefore a living machine. And so there is something fundamental that happens when we essentially look at how living machine works, is that they harvest information, matter, energy in a way that radically differs from the way mechanical machines do. So the linear metabolism of the modern city effectively evolves into these multiple interlocking metabolisms that is fundamental for the circular city of the future. And if we look at this from the point of view of a kind of urban diagram or infrastructure diagrams, this really means evolving from a diagram like this. This is Tallinn, by the way, capital of Estonia, where we ran a project from 2017. Claudia was a curator of the Biennale of Architecture there. So you evolve from diagrams essentially like this, which is centralized towards the main, in this case, wastewater processing plant, to a diagram like this, where every building, every public space, every element of the urban realm can become at the same time both a producer as well as absorber of resources. And therefore, a distributed system emerges where resources are exchanged in a non-linear way. So how can we then move forward and imagine the actual materialization of this new diagram? What form this may take? And here, of course, we had fun at the time generating visuals for a kind of flooded Tallinn in the future, which is now kind of reactivated by these new networks that are proliferating through the city. And that's like in the winter and in the summer. And this was kind of one of the close-up visions of this concept. But essentially, to understand a little bit more profoundly what kind of a switch we can implement, we went back to research. And one of the projects that was developed for several years in London, in UCL, in the Urban Morphogenesis Lab, was the study of this really unique organism, which is called slime mold. Some of you may have seen it already because it is a toy which several engineers and architects somehow have played with in the past, mainly because of his ability to simulate, if you want, or to grow in shape like that are very close to the networks that we observe in cities and in urban developments. But of course, the way this organism works and the way it achieves this kind of optimized network is completely different from the way urban networks have been engineered. And we can call it a kind of bottom-up process, but essentially it is based on the emergent collective intelligence of millions of nuclei that float within the body of the slime mold and essentially exchange with the biochemical composition of the local environment, the points where they find themselves, and among each other. And these, somehow without any planner, of course, without any form of centralized intelligence, is capable of generating optimization, forms of optimizations that are very similar to the one engineers have to deal with when designing urban networks. So the fascination with this organism, of course, went on or is going on for a few years, but this video is being developed with artist Heather Barnett, and it was really about capturing the organism not only for its morphology, but in its behavior. Because I think that it is when you observe the way the organism actually grows and optimizes itself that you realize the profound difference that it has with our let's say, with our instruments. So, of course, at this point, we realized that we can say the ecological intelligence of the slime mold materializes or manifests itself precisely in the convolutedness, if you want, of his networked body. And we can see it a little bit more, maybe. And the fuzziness of his distributed spatial memory. So the imprints that lives on the landscape that becomes part of its computational process. So these, they defy both the classical canon of beauty, if you want, of symmetry and proportion, and also the rational logics of efficient engineering. And this is, for us is intriguing because, of course, as I said before, there is no master planner in the process. It's bottom-up emergent collective intelligence. And I think this is a quality that is critical to urban design today, because it mobilizes collective agency and intelligence to face the challenges ahead, especially the accelerated dynamics that are imposed, in our case, by the current climate crisis. So we can see this as a metaphor, if you want, of how we may act as planners in the future, but for us it's more than that. It's really the possibility to develop new tools, new instruments for design. And so in that sense, we didn't really want to kind of scale up the slime mold as a sort of a metaphor to apply in the form of the city. And also, we didn't really want to just simply abstract the behavior of a slime mold and turn it into kind of biomimetic model, if you want, which basically would be like extracting a special case solution from a very human-oriented perspective. So what we try to do is more to engage, we can say, with the diagrammatic capacity of the living system itself in the process of growing. And so becoming part of what we may call an architectural or design tool. So these went through a series of stages. The first one we see before, like through designing or 3D printing a substratum on top of which the slime mold would grow. So in this way we could communicate data coming from a real city, a real site, to the slime mold and then kind of map back its reaction. We then went, of course, into developing interfaces like this one, which use a kind of algorithmic modeling to somehow connect the behavior of the slime mold to the redrawing of infrastructure. And this is the kind of workflow of these type of instruments. So essentially data come from sources like digital elevation model, GIS, satellite imagery. So the kind of amount of data we have covering the territory of the city. And then we go through a series of stages of mapping, extracting the abiotic analysis, and then network analysis, and then further down the line, urban morphology scenario. And in this particular moment, I think that's where the sort of new recent development of artificial intelligence have become quite interesting for us in a way. Specifically, we have attempted to use artificial intelligence algorithm has a way to learn the behavior of the slime mold and translate it into a tool. So we tried to train this algorithm, and in particular GAN, generative adversarial network, which are quite popular among designers, I think, these days, because they kind of have a kind of visual approach to them. You can actually work and play with them in a way very visually, to essentially train them to recognize the patterns of behavior of an organism like the slime mold, so behave like slime mold, and then use them to essentially process satellite images to generate scenarios of cities, or future scenario cities. So like fast forwarding our ability to imagine urban scenarios. This is some quick shot of recent work conducted in Innsbruck in the Department of Landscape Architecture, and directed by Claudia Pasquero, where I have worked as a visiting professor. Here is work on one project we did on the melting glacier of the Alps, and again trying to imagine the evolution of this landscape, fast forwarding it through the working of these AI images to imagine the ways of retaining this water and essentially maintaining the cycle with the communities that inhabit these areas that rely on the cycle of melting and refreezing of the glacier. This is the scenario we saw before, in which we started to look at the remetabolization of the pollutants contained in the electronic waste, and again fast forwarding the evolution of this landscape as a kind of filter, remetabolizing these pollutants. This is another case study. I'm going quite quick because this is just to give you an idea of how we are essentially applying these new techniques, which, to be honest, we are really trying to learn about as we go. And again, this is the landscape near Kathmandu in Nepal. And again, we trained the algorithm at recognizing these patterns in the landscape and then applied it on the area of Kathmandu, which right now suffers from a really, really heavy contamination of the water table and effectively makes the water unusable for most residents. And so we kind of developed a really high resolution maps of both the existing landscape and the distribution of buildings and dwellings in the area using the techniques I mentioned before. And then we tried to fast forward the redevelopment of the substratum of the city in a way that it would perform again this role of filters and distributor of the water. So this evolves essentially into a much more articulated new waterscape that enables the remetabolization effectively of the pollutants in the water. So I'm now moving towards the end of this presentation, but I think one of the key elements of what for us matters in trying to develop this new methodology is to evolve some of the concepts that essentially we have inherited from the modern tradition, but that are also very much connected to its linearity. So ideas like zone, boundary, scale, typology, and program, these are all concepts that in a way limit the possibility of a truly systemic approach to be implemented, because essentially frees the possibility for system to expand and evolve and to create this coevolution between the, let's say, urban and the natural system. So essentially for us it's really about not just evolving the technique, but also using these new techniques to somehow evolve the way we conceive the city and some of the key notions or logics, instruments for developing urban policy. And this is, again, the core of our collaboration with the United Nations Development Programme to create essentially a strategy that could be scalable and could be applied to as many cities as possible in the world without necessarily our presence being there all the time. And we are in early stages, so we have been applying now these techniques to a few case studies selected for us by UNDP. And we are collecting feedback from them, and that becomes a process that will hopefully enable us to evolve these tools in a kind of a impactful and useful direction. The project of Guatemala City, I think, is a significance among the one that we have analyzed. Well, first of all, per the very complex, highly unstable terrain surrounding the mountains and volcanoes, which is where Guatemala City is located, but also because its ecosystems that originally were very rich in biodiversity are now made fragile by unchecked urbanization and the effects of climate change, which are particularly evident in that climatic zones. In Guatemala City, this scenario is exacerbated by a serious lack of waste management. And this obviously is not just the case of Guatemala City, but here it's particularly evident precisely because of the geography. Guatemala City has a huge garbage dump, which is the biggest of Central America, and containing over a third of the total garbage in the whole country. So 99% of Guatemala City garbage sites have no environmental system or are classified as illegal. And again, the whole concept of legality, formality, informality is very blurred here. And I think that's also part of the work that we have to do to understand how our ideas of formal planning can begin to operate in this kind of bottom-up emergent regimes. Here, the waste is now a kind of geological layer. It's so much embedded into the geology of the city that will never be removed. It will have to be remetabolized in some way if the city has to continue functioning. At the moment, this is not happening, and these are some of the results. Incredible erosional processes that somehow all of a sudden appear as these huge holes in the middle of the city. And obviously, our approach is to try to create a new interface, if you want, between the bottom-up processes of self-organization such as the many local waste recycling activities that are emerging, often out of necessity, in the areas close to the dumping site, and the strategic decision-making that occurs at municipal, national, and international level. So some of these strategies that you see here in these diagrams are designed to essentially recognize, map, and plot this emergent activity, and on the other side, test how larger scale municipal strategies can be related to them. And we also developed a few scenarios that were somehow actualizing this idea, and this was a very nice I think, test project related to the idea of urban agriculture. And this is a video which we developed also with students in the YAC, one of the studios there, that tries to illustrate how this interface could be applied to a rewilding process in the city of Guatemala. I think what brings together these proposals is really their sensitivity to the local conditions, while at the same time trying to create a platform for this local condition to somehow affect national and international power relationships. So for instance, the migrating birds populating the green areas of Guatemala City migrate to and from Canada. They go all the way up there. So therefore, investments in the rewilding of the city of Guatemala could have benefited the biodiversity of the entire continent. Similar thing can be said for the migrant workers that cross the city on their way to US-Mexico border. Many of them are living depressed countryside, and new urban agricultural plans could retain rural workers, alleviating the pressure on the border. And so in this way, we imagine that such synergies may have the potential to channel significant investment funds from international organizations, and that's also the hope of the UN development program, to local projects improving the life of citizens, but also discovering new paradigm for the future evolution of these cities. These are some of the drawings. We also did our case studies, Mogadishu. I'm not going into detail with all of them because it's a long story, but the application of the method is the same, and from the analysis to a visualization of what it may be in the future. If I have still a few minutes, I will just conclude with one video, and that's it, so we can maybe open up a little bit the discussion. This is a video that describes a project we did in 2016 for the Venice Biennale on a site in Montenegro. I wanted to play it mainly because it relates to a context that is quite close to, let's say, the conditions on the site of the studio with the students here, and also to show that effectively our idea of city goes beyond the boundaries of dense urban areas and effectively reaches out to sites where the resources are extracted or effectively recycled or remetabolized. And so in that sense, it's a conception of the city that we have named effectively urban sphere, that it's encompassing every corner of the planet and is trying to really redescribe this kind of artificial dichotomy between city and landscape or rural areas. And I leave you with the video, which is a couple of minutes long.
The Sentinella is right now above us, scanning the landscape of the Salina city and sending data to the ground station in Matera. The Sentinella 2 has got a wide range of sensors that are able to capture different wavelengths Interestingly enough, you can algorithmically select different wavelengths and calculate or compute a series of drawings or maps that may allow you to see this landscape and the gradients and that are characterizing it. Is this the way birds see the landscape? Ornithologists are actually able to track some of the species that come to Solana through GPS trackers that they install on the back of some of these animals. And so the birds have become data feeds. From this perspective, the salina really appear as quite small. But if you zoom in, it could be nice to imagine the surface of the salina to corrugate, to become a lot more articulated. So imagine machines that operate more in the way birds operate, through swarm-like behavior. Maybe simpler machines or smaller machines that would be able to coordinate and to begin to develop behaviors in the shaping of the landscape, for instance, as some kind of ground machines or ground robots. It would be interesting to imagine how this could be embodied in architecture in the form of these aviary that are open because they don't have a net, but that create conditions for nesting and for interaction beyond what we know today. As you look at the crystals of salt right now, you can imagine these patterns to be affected by these emerging morphologies. Yes, and perhaps this whole process can be detected from the satellite itself.
Okay, thank you very much. Thank you.
Thank you very much. We've got just a little bit of time for a few questions, maybe 3 or 4 questions. As long as they're questions, if you make a big long statement, then we'll have to stop quickly.
Marco, thanks for a fantastic lecture. Really, you've set a very high bar for the rest of the year. So, I was absolutely fascinated by not only the kind of the way in which your designs are interfacing with buildings, but the large-scale work that you're doing as well. I've got 2 questions. They're kind of related to each other. The first one is around the interaction in the buildings and how those things can come together. I think it's such a clever way to put things together, but I wondered whether you had done, when we're looking at sustainability, we kind of look in the whole on these things, and I wondered whether you'd done any kind of embodied energy calculations around both the, what it takes to create the product and so on, and then maintain it and all of that kind of stuff, and how that comes out. And the second one at that larger scale is, I was fascinated by the rewilding in very large areas, but I suppose I was trying to understand what the materiality of what you were looking at. You started off with kind of slime molds and various other things like that. And I was thinking, what's the interface, the human biological interface that you would actually have when you've rewilded something? One can envisage a forest or something like that in a city, and you can understand rewilding in that kind of a context. But could you talk a little bit about perhaps the different forms that rewilding could take?
Yeah, thank you for the question. You can hear me, right?
Yeah, absolutely.
Okay, cool. So, definitely the first question relating to the, let's say, whole cycle of the project and this new system. Since we developed PhotoSynthetica, which is only the last 2 years that we set up this venture, we tried to work with 2 specific products. One is this membrane, which we call urban curtain, because it's kind of soft and light. And in particular, the whole idea behind this was to create a technology that could be deployed not just in new buildings, but also very much in existing buildings in order to be able to effectively give an opportunity for improving the performance of what is like 98% of the built environment, right? So the idea was to have something that is really lightweight and reduces to the minimum the necessity for substructures and therefore all the embodied energy of making that. And uses, for the moment, ETFE, which is obviously not bio-origin polymer, but at the same time it exists in recycled form and it is fully recyclable because it belongs to a very specialistic closed loop of material. And so we worked with Tayo, we worked with other manufacturers, Architect Landrel in UK, to effectively implement that. And of course, the other elements has to do with the lifespan and how long this can last. And in that sense, the ETFE was the best compromise for the moment. We also started to look at bioplastic material, which ideally at some point could be made for 80–90% from the biomass of the algae that grow within, which would in a way for us also beautifully encapsulate this idea in the product. But let's say for now, the bioplastic we found that is suitable for that scale of application still comes mainly from the packaging industry. So this is material that can last for 2–3 years maximum. So that works very well for projects that have a temporary use. So then we did that test bed with the scaffolding, for instance, because one of the applications was really related to the possibility to upgrade and improve the performance of building sites during the construction, especially for large, long-lasting building site. So essentially, that's our kind of reasoning, and that's the direction that this product has taken. And so the optimization of the whole process is happening step by step, but it's based on this idea of kind of a circularity of material and lightness. Then, of course, in itself, captures CO2 and grows biomass, which also will become part of new supply chain. So ideally, and this is something that obviously still have to occur in a larger scale beyond our test bed, but ideally it will basically enable and perhaps even trigger new local industries, if you want. And so the idea is that precisely because it is not, the algae are not growing somewhere in the middle of the desert in an industrial plant, but are growing within the urban realm, that would create new closed loop industries to emerge, and therefore, further contribute to the reduction of emissions to actually make and import products of different kind. Especially packaging is a very promising industry. We started to work with Nike on developing strategies of application of that, and they were very interested in especially in that side of the story. So that's the direction of this. The other let's say product was the 3D printed version, which is in a way still more in a kind of experimental realm. So normally we start with kind of more artistic applications, which allows us to test the technology, push it, but also bring the discourse to a wider audience. But that also has a really great potential because we can already 3D print with biomaterials, so bioplastic. The possibility to create this extremely lightweight, intricate structure really puts the algae in the best condition to work, especially when we think about filtering pollution, which is one of the most, let's say, common requests we have from early adopters or clients that are interested in this. It's often about the issue of filtering and absorbing particulates. So that's another direction that can optimize multiple aspects while still allowing for, which for me is also very important, a kind of new architectural expression of this. I think both the urban curtain and the 3D printed elements are trying to create a new kind of interface, which architecturally speaking is really about softness, and it's about convolutedness. It's about creating opportunities for nature to inhabit this gap between let's say the built environment and the realm. So there is a kind of idea of biodiversity or enhanced biodiversity there, which hopefully begins to answer also your second question. Because obviously the infrastructure work, it's a very large scale. Maybe the two are still kind of disconnected formally, if you want. But the idea is very much to create a link whereby these membranes and this new way of articulating architecture create gaps, not just for algae, but many, many other organisms, both micro and macro, to inhabit these new networks. So, of course, plants and nature that we used to see will be part of that mix, but we think about that being articulated in multiple scales, not just one or two.
Okay, we have one more question.
Sorry, my answer was too long.
No, it's okay. It's like another lecture. Yeah, okay. One here at the back. I'm going to run.
Just following on that last point about the scale, I was wondering when you're talking about, well, you had the slide up talking about the city planning and how, it's the wrong model for all these systems. If you considered that this system you created as a metaphor at that big scale, how would you create a system that can be managing its growth pattern, if you like? In other words, rather than just an algorithm, could you use something like blockchain systems or other AI as a way that it becomes something that's linking the society with that bioecology AI map that you're generating? Yeah.
No, I think certainly that's the kind of part of the long-term vision. At the moment, really what we are developing is targeted quite closely to the request that we had from UNDP, which is our partner in that project. And so for them, it's very much about creating a kind of planning interface that is scalable and can be brought to their local branches, which are located in almost any city in the developing world especially. And therefore kind of bring the sort of city planners and the kind of leading, let's say, local community leader around the table to study the city from a different perspective. But then, of course, I imagine that once that phase would be applied, and so we would have that conversation happening with these multiple tables, then you can begin to bring in technologies that create the other, let's say, type of interface, which is the kind of embedded in the urban infrastructure, in the urban realm, more directly. And so, I mean, that is, for instance, already implied in our mind also in the installations that we have done. So the PhotoSynthetica project really brings the hardware, wetware, and software together. And so the hardware being the actual membranes themselves, and the wetware, of course, the living organism with their sort of biological response. But then there is the software elements that is about, of course, monitoring the system, but it's also about communicating data with other systems and therefore become part of a larger network, which then, of course, there are different ways for implementing it, and technology you mentioned, like blockchain, etc., could be one of those, precisely because they are all about the kind of distributedness and the kind of decentralization. But to be honest, this is a kind of I think it's a step still further down the line. But again, like there are, I was just recently at one of the conference organized by UNDP, and there are several professionals that are engaging with that level also. So I think at some point, probably the most effective way would be to create an extended network also where different technologies are brought together. I think ourselves, we're very much operating in this level of the design interface. I think that's where our strength is. But the system we are imagining are somehow developed with this idea in mind. So it will be a matter of implementing that system at some point. But yeah.
Okay, on behalf of the Melbourne School of Design and the Faculty of Architecture and Engineering, I want to thank Marco for a very fascinating and speculative lecture. Thank you, Marco.
Thank you so much. Thank you very much.